Okay, so we're going to talk about MIP equals NX. This result that multiple interactive provers are equivalent to non-deterministic exponential time. And this is proven by Babai, Fortnow, and Lund in 1991. And the first direction of this, the fact that multiple interactive provers can be simulated in non-deterministic exponential time, is not so hard. You could do it on your own if you've taken a complexity course. And there's lots of stuff online if you just look up MIP equals NX. Basically everywhere you can see how to do it. It's essentially the exponentially long certificate is a record of sort of a transcript, a possible transcript of the questions you could ask to your multiple provers. You can figure it out. So a little historical context for this result, though, first, is in 1990, and all these dates, it's hard to really tell because, like when things are first published or when they're first proved, it's all, but definitely Lund, Fortnow, Karloff, and Nissan proved this sharp set is an IP result, which is P to the sharp P is in IP, yeah. And then 3 weeks later, Adi Shamir extended that result to get the full thing of IP equals P space, which was huge, a triumph in complexity theory. And pretty soon after that, Babai, Fortnow, and Lund, so Fortnow from here and Lund from up here also, proved that MIP equals MX. So multiple interactive provers actually give you, well, probably more power than a single interactive prover, as long as P space is not equal to NX, which we would assume that it is not. And because, I highlighted that Fortnow and Lund both worked on this sharp set result and this MIP result, you might guess that this MIP result is actually kind of based on this sharp set, and in fact it is. So let's revisit that. This is the so-called sum check protocol that Lund, Fortnow, Karloff, and Nissan came up with. And basically what it was is it's an interactive proof that if you take the sum over an inputs of a multidimensional polynomial, and it's all the 0, 1 inputs, it's an interactive proof that this sum is equal to some value. And if you think back to the sum check protocol, right, what you might remember from learning it is that it has these two properties we really need. We need this sort of restriction, like each time you peel off this sum and you replace it with a bunch of constants inside, you need this restriction to be low degree. And the reason for that is because if it's low degree, then you know that it's then the dishonest prover doesn't get lucky, right? Where it's coincidentally the two polynomials are equal very often, because low degree polynomials can only intersect at, or polynomials in general can only intersect at as many as the maximum degree of the two of them. So they're not equal if it's low degree with high probability. And then the second thing is, this is all well and good, right? This is like the property we need when we're doing sum check and we're going through the thing and we're making sure that incorrect claims go to incorrect claims and correct claims obviously can go to correct claims. But then at the very end, we need to do some sort of test, and we do this so-called the final test, right, where we actually evaluate this polynomial. And so the verifier needs to be able to evaluate it in polynomial time. And it's this second point that seems like it's probably the main issue for NX. Like, we have this exponentially long computation that we're trying to capture. And how can we do that how can we evaluate it in polynomial time like this? It just seems impossible. And you're right, I mean, we probably can't. But it turns out that with multiple provers, we get this special power called non-additivity. Normally you think of, okay, I'm going to ask a prover a question, and then it responds, and then I ask another question, and it can base its response to my second question based on what my first question was and what its answer to my first question was. But with multiple provers, we can actually make this not the case. So we can make it so that the prover acts like an oracle, which just holds some function that maybe depends on the input, but not on the verifier's questions. So if I ask it question one and then I ask a question two, it's going to give me the exact same answer as if I asked a question two first and then asked question one. Or, yeah, right. And the kind of idea for this proof, we're going to go through all the details of this later, so no worries, uh, is that you can check these answers against each other. Is you can ask a bunch of questions to one verifier and then go to the other verifier and say, hey, what do you think about question 15? And if the first verifier was cheating by by adapting to your questions, then the second verifier has no way of adapting because it's only seeing this 15th question. Uh, and so it gives an answer. And if the first one was cheating, then with some high probability, then the second one will have to differ on. Um, but this has this issue of, okay, so we can enforce non-adaptivity, right? Our oracle can holds this function, but how do we know that the oracle is holding the correct function? Right? Like this is a big problem. This seems like an unsolvable problem in this case, right? Because if we're not holding this polynomial, we have like no way of knowing that it's even related to the polynomial we want. Like what even what do we even care about? And it turns out that when we arithmetize nx, we actually get this special kind of language. So I'm going to talk about this some in a little bit, but what I want to emphasize here is that x is in L in this arithmetization if and only if there exists some function a such that this is true. So a this gives us like a powerful tool. We don't care which function a it's storing, but the very fact of it storing a function like this proves that our input is in the language, right? This is a great tool way of thinking about it. So we're no longer really caring about a specific polynomial. We're caring about, is there a function? Is there an assignment of these variables? Because what we end up doing is we think of, there's some other inputs we'll get to later, and then there's these three inputs which you can think of as like the variable names of a three-sat clause. So these are polynomially long bit strings, which can represent exponentially long many variables. And then a is the assignment function, so it maps each bit string to 0 or 1. And so we're actually asking, like, is there a valid assignment for this function, right? Makes sense. You can see where the nx is coming in. Cool, great. And there's actually a note, right? We don't, because in the original sum check protocol, we don't actually only evaluate on 0, 1 inputs. We have to evaluate on some large finite field to do these consistency tests. So we actually asked the oracle to hold the unique extension of A over our field. So we have, n dimensions, and it's linear in each dimension, basically, is what we're saying here. And if you can prove that this is unique on homework, it's in the original paper if you want, but I think it's not that bad. Note that this does not mean it's literally linear, because the total degree can be up to n. It's just linear in each variable. So no variables are raised to, raised to any power other than 1 or 0. All right, let me get some water. So, and it turns out that actually, because we've been asking about, okay, we only care if there exists some A, we can actually weaken our assumption about the oracle. Because checking that it's actually multilinear seems like it's going to be really hard, and in fact, it's impossible. But checking that it's approximately multilinear, like it's in this sense of there's some multilinear function that is equal to the function that the oracle stores on all but some small fraction of the inputs, is actually sufficient. And the reason for this is because all we're trying to do is check that there is some multilinear A. So if this A is close to some multilinear A, then it's almost almost the same. It's proving this existence for us, even if it's lying. So we actually can, and this is a big contribution that PyBy and Lund did, we can check if an arbitrary function is multilinear, or is delta approximately multilinear, right? It's close to, it's equal to some multilinear function on all the delta fraction inputs in polynomial time, with confidence like e to the negative delta, basically, which is really good. So the steps we're going to take are basically, first we have to arithmetize this nx problem, and then you want to verify that the oracle's function is delta approximately multilinear. Yeah, I guess I should write multilinear here, not just linear. Let's see, multilinear. And then you run our sort of modified subcheck that we're going to do on the above, on this arithmetized formula, and you use the oracle's function to approximate do the final test, and you're good. So theoretically, we're done now. In practice, of course, there's many details we're going to have to go through, and so what we're going to do is do this sort of in 1-3-2 order. So first, we're going to talk about how to arithmetize. Well, first, actually, we're going to talk about some basic results about multi-interactive provers. Then we're going to talk about how to arithmetize an exp and give an nx complete problem and then arithmetize it. Then we're going to talk about how to run sum check with oracles, and then finally we're going to talk about verifying multilinearity. Okay. So, here are some MIP results about multiple interactive provers, and actually you can try if you want proving these on your own. I think it's maybe a homework problem in an undergraduate complexity class. You would maybe bang your head against it for a while, but it's definitely doable. So our definition of multiple interactive provers of MIP is that L is in MIP if there's some verifier B, some polynomial verifier V, it's a polytime probabilistic verifier. It's such that for every string X, if X is in the language, then there's some set of provers such that V interacting with those provers will accept with probability 1. And if X is not in the language, then for every set of provers, the probability that the protocol of V and these provers accepts is less than 1/2. And this constant is arbitrary and clearly can be boosted for the same reason all of our probabilistic constants can be boosted. You just run it multiple times. And the provers are unbounded power. Actually, it turns out you only need exponential power in these provers, which is kind of cool. You can imagine why that would be, knowing that MIP equals nexp. Yeah, but I'm not going to talk very much about that. Okay, so the first fact we're going to say is that if the protocol, and so before I show you the proof, if you want to try to prove this on your own, this would be a good time. So I'll say it out loud. If the protocol uses polynomially many provers, it can be simulated with 2 provers. So this is a nice result. You only need 2 provers. The original paper is actually called Non-Deterministic Time, has 2 prover interactive protocols. So it's nice, and it's nice to think about multiple interactive provers as only having 2 provers in certain situations. I also want to note that this actually means arbitrarily many provers can be simulated with 2 provers, because the verifier has to run in polynomial time, so it can only ask polynomially many questions, and then it can only ask at least 1 question to each prover, unless you have you have to do a little careful analysis saying, okay, well, a prover does not ask any questions is equivalent to having 1 fewer prover. And so, yeah, this is actually saying any number of provers can be simulated with 2 provers. All right. And the proof of this is basically this protocol. It's I think, easier to explain than it is to write out. Basically the idea is that if you're given some multiple interactive prover protocol, you want to simulate with two, what you do is you basically you pretend you're the verifier, you roll all of your coins, you generate all your randomness, and you send all of that at once to the first. And the first prover sends back to you what you would have the whole transcript of the interactions you would have had if you were the original verifier talking to K provers. So it shows you the exact record of the conversation. And then if that conversation leads you to accept, then you pick one of these provers at random and tell the second prover, okay, you're now prover I, right? With I is in 1 to K. And you you basically you just ask prover 2 all the questions you asked prover I in this transcript, and you right. Excuse me. And then you just make sure that this second prover is actually accurately recreating the transcript of prover I. And this is great because if uh, clearly if there's some provers that work, we can simulate that. But if there's no provers that work, we can't actually get tricked because if P if our like second prover that's simulating the ith prover, um, yeah, basically if there's no independent provers, then to trick us into accepting, we know our first prover has to be lying about this conversation somehow. But we know that the second prover's strategy, like it has some behavior if you tell it it's the first prover, it's some behavior if you tell it it's second, third, fourth, ith, kth prover. And so that would define a valid set of provers, unless P2 disagrees with P1 on some input for some question. So we're going to reject with probability 1 over at least 1 over k. And then from above, this constant is arbitrary. We can clearly boost that to whatever we want. Okay. Our second result about multiple interactive provers is that L is accepted by what we call a probabilistic oracle machine. If for all if X is in the language, then there is some oracle that the oracle machine accepts, right? And if X is not in the language, then for every oracle, we have the probability of accepting is less than 1/2. So this is a little different from what you might think of as oracles in complexity theory. Because typically we think of oracles as, we're totally trustworthy. So this is a different thing. This is an untrustworthy oracle. And it's essentially, this is getting very close to NX kind of, right? It's not quite the same because you don't have this power. In NX, you have an exponentially long witness, but you also have exponential time to process it. Here, you can have an arbitrarily big witness, right? The oracle's proving it, so you can ask it questions. In practice, it's only exponentially long because you can only ask it polynomially long questions. Um, but you don't have exponential time to actually verify it. So we'll talk about how we get around that in our in our full protocol. Um, but it turns out that multiple interactive provers are equivalent to these probabilistic polytime oracle machines. Uh, and the proof of this is quite simple now that once we've proved this above. So if L has a probabilistic polytime oracle machine, you can just have the verifier ask each question that it would ask to the oracle machine to a different prover. And then the provers certainly can't adapt because each of them is only getting one question. We're asking only polynomially many questions, so it's all okay. Um, and that will define almost an oracle, and will either be in this situation or this situation. Okay, and on the other side, you can basically just ask the oracle to uh, simulate additivity by prefixing each question you ask it with the total history of questions you asked it before. So, turns out these two things are equivalent systems. Cool. Equivalent, we can mix them. So what we actually will end up doing in this protocol is we're going to have one oracle, and we'll run the sum check protocol with this prover, and then at the end we'll ask this final consistency test, or the final test rather, to the oracle. Cool. All right. So we have our basic MIP results, MIP results. I can't decide which one I like saying more. This is another benefit of making lectures on this topic, is maybe we'll introduce some lexical consistency. Okay, so now we need an arithmetized NX complete problem, our oracle sum check, and then verifying multilinearity, and we're going to do them in this order. Okay, so arithmetizing NXP. First, we're going to talk a little bit about Cook-Levin, and then we're going to give. There's basically the NXP equivalent of Cook-Levin is almost the same. So it takes this. Cook-Levin takes like an NP machine and creates a poly-size Boolean formula that is satisfiable if and only if the NP machine has a valid accepting path. And the summary of how this works basically is you make a variable for like each tape location and like each location on the tape, direct product with the times of the computation and the symbols. So each of these variables looks like, okay, in tape location 8 at time 10, I'm going to have the symbol, J. And then you have some other variables for other stuff, like at each time, where's the head, and at each state, at each time, what state are you in? And then you create all these clauses like, okay, we need to have at most one symbol for a tape cell, at least one symbol for a tape cell. We have to finish an accepting state. You have to transition according to your transition rules, etc. But the thing is, these are all actually like pretty simple. And actually, the Wikipedia page on Cook-Levin is really good for reviewing. They have this, if you go to the proof section, they have this really nice table that just lists out like, okay, here's all the variables and all of the types of clauses. And reading through them, you're like, okay, yeah, this makes total sense. Like, obviously, this is true. Cool. So this is polynomially many clauses, polynomially many variables. This still all works for an NX machine. It's just we have exponentially many variables and exponentially many clauses. So this seems like a problem, but it turns out it's not as big of, well, I don't know. I don't want to say anything. It's still a problem. But we can give the variables, if we have exponentially many variables, as we talked about before, you can give each one a polynomially long name. And then each clause will have a polynomially long description, right? If each variable has length s, the name has length s, then our clause we can clearly describe with 3s plus 3 bits. In kind of this manner right here, right? Where so you have these t's that describe like, not or, well, whether we're putting a variable or its negation in the clause. So if this is 1, maybe it's a not symbol, and if it's a 0, then it's just the variable. And then these bit strings describe what variable we're in. And so from this NX Cook-Levin, we have this 3CNF for any input W, such that phi W is satisfiable if and only if W is an L. And all the clauses are like this. And a cool thing about this is like if you look at the kinds of stuff in these clauses, it's like it's not very complicated stuff. Like it's you can imagine you can you could write Python code very quickly to figure out is this clause valid or not. So there's actually right there we can compute whether each clause is in our formula time deterministic machine clause that takes this description of a clause as input and it outputs one if the clause is phi and zero if it's not. Okay, so this is great. So if what we kind of want to do now is we want to create a formula where it's like each clause we can clearly evaluate very quickly, and then we can evaluate whether the clause is in it. So we can do both in polynomial time, which is good. So from normal click 11, we can arithmetize this clause, this deterministic machine clause. Um, yeah, so that basically, so that there's some z, so that you get some formula psi of w. So there's some z that satisfies psi of w, if and only if the clause described by t and b is actually in our formula. And it turns out because clause is deterministic, right? If you look at what we actually do in Cook 11, it's like describing these computation paths. There's exactly one valid computational path because it's a deterministic machine. So that's cool. If you take, well, as we will do later, if you take the sum over all possible z's, then we can actually just change this straight up to a sum sign, and you get this exact same thing, where it's equal to 1 if it's true and equal to 0 if it's not true. So now we're going to describe what I call bad outcomes. So FW is a bad outcome if the clause TB is false under the assignment A, okay, and the clause is in phi. So that means our if we have a bad outcome, our formula is false. And this z is again this like extra non-deterministic thing we are putting in to arithmetize our polynomial time machine. And I hope it's clear to see that a formula to compute this FW is this. So it's just not of the clause, right? So the clause is false, and the clause is in the realization of the polynomial time clause machine. Okay, great, cool. So we know how to turn this into a polynomial. Like this is we've covered this in SumCheck, and if you watched the IP equals P space lecture, you know the result. There's some polynomial that agrees with this Boolean formula on all 0, 1 inputs. So we call that PW. And then we get this sum. So this sum over Z, PW is bad, PW is equal to 1 if clause is bad under this assignment A. Great, that's exactly what we want, and it's 0 otherwise. So then we can just take the sum over all possible clauses, and then we get that this whole sum is greater than 0 if phi is not satisfied by A, and is equal to 0 if phi is satisfied by A. And of course, this phi depends on the input, so I should remember to write that. Great. this is amazing. And another thing to notice is just that the degree of this polynomial is polynomial. It is bounded and polynomially. And you could verify that for yourself if you just look at this formula. You know that this is polynomially bounded because it's a polynomial computation. This is clearly a polynomial. We'll turn it into a polynomial degree. Polynomial of polynomial degree. It's a little confusing, but yeah. Okay, great. So what I want, maybe I should just take a brief step back here and say, remind us what we've done, which is we've turned, for any NX problem, the question of, is W in our language, into this statement of, is this sum over zero inputs of a polynomially degree? Okay, that's great. That's exactly what we said for you. All right, moving on. Sum check with oracles. So, as I said before, we need the oracle to store this function a for us, or this variable assignment. And we need to evaluate a on a big field, a big finite field, not just 0 and inputs. So we ask the oracle to hold the of a. Yeah, I'm not sure why I wrote it on 0, 1 inputs. It's just the multilinear extension of it. Cool. And as I said before, I think if you want more homework, you can prove that this extension is unique. And again, I want to emphasize this is not actually a linear function, right? It can have degree up to n because you can multiply each of n variables together. It is multilinear in that if you look at it from any individual variable sense, it's linear. Like there's no term where you get an x to the I, x sub I raised to the second power, to the third power, or to any power other than 0 or 1. So if A is actually multilinear, then this polynomial h, which just kind of swallows up A, is also low degree because it's polynomial degree here, and this is polynomial degree, so composition, you get still polynomial degree. And our goal is, basically to give a Oracle interactive protocol to verify that this polynomial is equal to some sum, and in our case, 0. What we're actually going to prove is saying, okay, if this equation holds, then there's a prover that will convince us with probability 1. Cool. If the prover holds a function that is somehow close to a low degree polynomial h, then we reject with high probability unless okay, I'm not doing a great job, but basically unless the equation above holds with essentially we have this property. I remind you, we're just trying to show that something exists, right? So if it does hold, the prover can convince us, and if the function is close to a low degree polynomial, then it still convinces us that there is some low degree polynomial that satisfies this, which is all we care about. And what we mean by close again is this is equal basically on all but some fraction of inputs. So we say a function f is delta approximated by g on a field f if the proportion of inputs such that f is not equal to g is less than delta. So, the fraction of these bad inputs over the whole field is less than delta. Okay. So, what we're actually going to do is we're just going to say, let h be the function held by the oracle. Suppose it's delta approximated by some polynomial f that has degree d. Then what the protocol is doing is the Oracle improver are trying to convince the verifier that there is a degree d polynomial, we'll call it g, such that the sum over all these inputs is equal to k. And the protocol we're going to use is that it's exactly the same as SumCheck, except at the final test, the verifier asks the Oracle to evaluate h instead of evaluating g directly, because, again, we don't know what g is. So completeness, right, if this is true, if there is such a g, then an honest Oracle improver can clearly convince us of this, right? The Oracle holds g, the honest prover does SumCheck correctly, like the way they're supposed to, and we get a correct claim at the end. Soundness, as you may imagine, is a little more complicated, but it's actually not so bad. Let's call the field we're working on f. SumCheck. So when we get to this final test where we are going to query the Oracle now, but right before that, before we do that, we're left, if we start with an incorrect claim, right? So there is no g such that this is equal. Then we're left with an incorrect claim with probability, with high probability. So we have a correct claim at the end, right? Where this, and by correct claim, what I mean is that this is true for this polynomial f with very low probability, right? N times nd over the size of the field from SumCheck. If you can go and review your SumCheck protocol. That's just consistency tests, and you do them n times, so this is union bound. Then now, h is equal to f, right? So if the h, the function that the Oracle actually holds, is equal to the function f, that's low degree approximation, then we fail this final test, because the claim they made was there's no polynomial that has this. And so low degree polynomial. So we fail. So the only chance the Oracle has to trick us is if h does not equal s, which happens with probability less than delta, because of our definition of delta approximation, right? This is the whole point of saying only a delta fraction of inputs are wrong. Okay, that happens with probability less than delta. So again, just use the union bound. We're tricked with probability less than nd over f plus delta. So this is great. This is a low probability. If we can make delta as low as we want, we can make this as low as we want, basically by, I mean, yeah, this is some constant, and we can just repeat the protocol to amplify our correctness to become more correct. Okay. So a little bit of a weakness here is that you have to assume that the Oracle's function is low degree. And also, you might have some worries about this protocol. I mean, I know I did, because it's like, well, wait a second, there is a g such that it equals 0, right? They just set g to 0. And that's true, but as you saw above, like what we're actually plugging in is this polynomial pw, right? That has, and we're querying the Oracle for this a. So we know how to compute pw, and we're just asking if this exists. So we have this additional constraint for what kind of polynomial we're looking for, but that actually does not change anything about the analysis. So it still works. And so now let's talk about this final protocol. So you arithmetize. We've arithmetized it, so you get this thing where you take sum over b, and we're just trying to figure out whether there is some a such that this. We ask Oracle to store the multilinear extension of this variable assignment, and we verify that it's delta approximately multilinear, and then we run the Oracle SumCheck. Perfect. We're done. Like this is great. This is basically the whole this is the whole protocol. Modulo this one tiny piece of verifying multilinearity, which will take, as you can maybe see based on my scroller, more than half of our time. Maybe about half. Okay. So, first we're going to need a lot of definitions. So this whole test is going to happen over some basically an interval of integers because eventually we're going to and the reason this is okay is because eventually we're going to evaluate everything on like a large finite field. So some integers mod p for some large prime p. And so if we just prove this over an arbitrary interval of integers, we get this. So we're calling it big N, 0, 1, 2, all the way through big N minus 1. So it's size big N. And let's do some definitions. So what we're going to call a k-dimensional subspace, what you might typically call, like here, an aligned affine subspace. So it's not actually a subspace in the way you typically talk about it. It has these two characteristics. One, it's aligned. So if in 3 dimensions, the only subspaces are lines that go straight up and down, or straight at you, or straight left to right, or planes that are, some combination of those, or the whole space. Um, and it's affine, so they don't have to pass through 0. They can be offset by something. And right, the actual formal definition we can give is it's k-dimensional if there's n minus k coordinates such that basically every element in the subspace is equal on these n minus k coordinates. So it's fixed on n minus k coordinates. It can vary in k coordinates. We call it a k-dimensional subspace. Cool. And we say that a function is multilinear if its restriction to any line, any of these one-dimensional subspaces, is linear. And we say it's a delta approximately multilinear if it is delta approximated by a multilinear function. Perhaps not surprising. And something we're going to use a lot is these words correct and wrong. So we're going to say a line L is correct if A restricted to L is linear, and delta wrong if A restricted to L is not delta approximately linear. So this just gives us a handy guide, basically a way of grasping onto these lines and figuring out how linear they are. So the actual test we do is pretty simple. I think it's one of the things you would think of if you're like, oh, how would I test if something is multilinear? So we start with the line test. Basically, you just pick a certain number of points, and you say, do all these points lie on a line? And we pick m1 plus 2 because the first two kind of define the line we're checking, and then it helps our analysis if we just m1 more. With each of them, we say if L is delta wrong, then there's only a 1 minus delta chance that each one of our extra points lies on this line. And that's less than e to the negative delta m1. And this is because delta is less than 1. You can do this on your own if you want to verify this inequality. Cool, so that's the line test. And then the whole test is you just say, for each direction, right? So each dimension has lines going in that direction, right? Some are going up and down like this, some are going straight at you, some are going left to right. If we have more dimensions, they're going in, the 4th, 5th, 6th dimension. And basically you just perform this line test on some random subset of the lines going in the ith direction. And you accept if every line accepts, and otherwise you reject. So obviously if A is multilinear, this passes because every single line is correct. So you never encounter a wrong line. And what we're going to say is this proposition that if there's some some direction where more than like an epsilon fraction of the lines are delta wrong, then the test accepts with low probability. And this low probability we mean is like less than e to the negative epsilon m2 plus e to the negative delta m1. Cool. And prove this proposition is, well, so if this is true, then the chance of both like on the wrong lines is very small. It's this 1 minus epsilon to m2, which for the same reason as above is less than e to the negative epsilon m2. And then if we have selected a wrong line, the probability detected is, or sorry, actually, I guess the probability it's not detected, I should say. Let's change that. Yeah. Right. Okay. The probability it's not detected is less than this negative e to the negative delta m1. So by union bound, you just add them together, you get a bound on the probability that either one happens. Let me, geez, so many typos. You get them with this small probability. Okay. What this means is that if we pass the test with very high confidence, we can infer that in every direction, the proportion of wrong lines in that direction is less than some small epsilon. And you can see this because if you set m2 to be, if you set m2 to be t over epsilon and m1 to be t over delta, to e to the negative t. So this is great. Like you can just jack up these m1 and m2 polynomially big to get a like exponentially small probability of having, not having this property that some polynomial small proportion and polynomial are wrong on polynomially. That's great. Okay, so the rest of this lecture is then showing that this result implies that A is close to multilinear in overall. So you can imagine, right, it's not actually obvious immediately why saying, okay, well, most of these lines are linear on themselves by themselves, but how do we know that that means that there's some, there's some multilinear function that sort of stitches them all together? And I don't know, it's even hard for me to think about like my intuition about should this be true or not. On the one hand, it seems like maybe it shouldn't be true because each of these linearities are kind of unrelated to each other. But on the other hand, they kind of are related to each other because if you think about it, I have all these lines going up and down right next to each other, and a lot of those are linear, or the function is linear on those lines. And then they kind of have to be stitched together because the lines crossing them are also all linear on this. So there's some like weaving almost that's going on, and that's not really the way we prove it, but maybe it's a reason you might believe this before seeing the proof. Okay, so the way we end up proving this is first we give these two lemmas, this self-improvement lemma and then one called a pasting lemma, and then we do this kind of tree-based induction to finalize the proof of to finalize the whole proof. Okay. So, the self-improvement lemma. This says that given a function a from either n to the rational numbers, assume, that in every direction, proportion of delta wrong lines is less than epsilon, and a is 1/2 approximated by some multilinear g. So a is 1/2 approximately multilinear. Then our claim is that actually, because it has this property, G is actually epsilon prime approximates A, where epsilon prime is this quantity here, 3n squared plus epsilon plus delta plus 1 over I. It's a little bit of a mess, but it's true. And this is great. Basically, what this lets us do is later when we are doing this induction, we otherwise have this kind of devaluation of what we mean by approximate. But this self-improvement lets us, as long as we don't devalue it past 1/2, we can always get back to our epsilon prime approximation. Okay, so the proof of this lemma is a little involved, but it's cool. So the first step is we're going to define these 4 subsets of our whole space. The first one is bad points, so these points where A is not approximated by G. And what basically this whole thing is trying to say is that the size of B, the set of bad points, is less than, epsilon prime times the size of IN. Okay. Then the next set we define is W, which is the union of all delta wrong lines. So we're going to call these wrong points. And obviously, these are going to have sort of significant overlap because a lot of bad points are on wrong lines. By our assumption, there's less than epsilon lines in each direction, and so in total, the size of the number of wrong points is less than n times epsilon times the number of points in general. Okay. And we're giving these little bounds on these things because eventually we're trying to bound the size of this, and we're going to relate the size of this to the rest of the things. Okay, n is points on a line that is delta linear, but the h that approximates a restricted on L has h of x minus a of x. So this is, I guess I should actually say points x, because it's these points that are sort of the bad points on good lines. Not wrong lines. Uh, and so because this uh none of these points lie on wrong lines. And so because they lie on n lines and each line has a most delta fraction of its points misplaced, right? Because otherwise it would be on a wrong line and it would just be in the set W. Um, we get that m is less than n times delta of the whole set. So the proportion of misplaced points in the whole set is less than n times delta. Okay, in our whole space. And then our final set, we'll call it H. This doesn't have like a good catchy thing. I was thinking about trying to call them lucky points, but that felt like too many L's for, we already have lines all over the place. It's not that, but basically the idea here is that if A restricted to L is approximated by a linear H, but H is not equal to G restricted to L, but still A of X is equal to G of X is equal to H of X, right? So, okay, this is a whole thing. So it's on a line. There's a point that is on a line that is not delta long, but it's not approximated by G. But still, this exact point is approximated by G. So the point of this set is a little confusing, but there's clearly at most one such point per line because two linear functions that are unequal to each other intersect at most once. So we get that the size of h or is less than n over number of points in every line has this number of points times the size of the whole set, or the proportion of points in h over the whole set is less than n over I. Okay, so now that we've defined these four sets, we're going to do this proof. This first step of this proof is defining a set S, which is going to be bad points that aren't on wrong lines and aren't misplaced. And so you might think about like, okay, what are these bad points that aren't on wrong lines and aren't misplaced? It's an interesting thing to think about. And then we're going to define the closure of S as basically the union of all lines that pass through S. So the way I honestly have been thinking about this is if you have like some bundle of points in the middle of your space, you can imagine like this sounds silly, but like literally like dropping string down in every location. And if it hits your set, you like hold on to it. Otherwise you just let it fall through. And if you drop these strings in every direction, the intersection of all the points that the strings pass through is going to be the closure of your set. And there's this claim right here that I'm not going to prove because it's like a really unrelated and has like these two kind of complicated proofs. You can look it up if you want. It's in the original paper. It's originally proved. Bavai has a proof of it that's sort of more group theoretic, and there's a graph theoretic proof of it also by Algis, I believe. But it's this little lemma that basically says if the size of S is less than half the whole set, the whole space, then the closure of S is at least, at least a little bit bigger, at least 1 plus 1 over 2 to the n times as big as the original set. And I mean, it makes sense that every way you close these sets, like you're exposing yourself to more lines that you have to add. So it makes sense that this is true. Okay, now a claim that we are going to prove is that the closure of S is a subset of everything in the closure of S is either bad or misplaced, or is in this lucky set where it's coincidentally equal. And the proof of this is that if we take a point Y that's in the closure of S, and you assume that it's not bad and not misplaced, then we're gonna show that it is in this set H. So let L be the line that passes through S and Y. We know that there is some because Y is in the closure. And then call X one of these points on one of the points on the line. So we know that because X is in S, if we recall the definition of S, it's all the bad points that aren't wrong and aren't misplaced. So it's not wrong. So the line is not delta wrong. So there is a linear H that delta approximates a restricted L. Okay. So then we see that X and Y are both not misplaced. So H, and we know they're not misplaced because Y is not in this set M, and because X is in S, so it's also not in the set M. And so because they're not misplaced and they're on this linear line, we know that H of X is equal to A of X and H of Y is equal to A of Y. But something we do know is that X is bad and Y isn't bad. Because again, X is in this set, so it is bad. And Y is not in this set, so it isn't bad. So because X is bad, we have G of X does not equal A of X. And because Y is bad, we have that G of X is equal to A of Y. So G is not equal to H because H of X is equal to A of X, but G of X is not equal to A of X. But we still have that H of Y is equal to A of Y, and G of Y is equal to A of Y. So G of Y is equal to H of Y is equal to A of Y. So Y is an H. So this is kind of a weird way to set up this proof, but and maybe now you can believe me that this is like a meaningful thing to define, if only to think about this function. And so now we set up this whole inequality. We're trying to get a bound on the size of S. And really what we're trying to do is get a bound on this quantity, the proportion of i's that are in S. So we start with this lemma that I didn't prove, and then we know that the closure of S is less than S union W union M union H. And we know this because B is certainly inside of S union W union M. So we get S union W union M union H union M union H. So that's where those come from. And so we know that this is definitely the cardinality of this union is less than the cardinality of all the sets combined. And just using, we already know some bounds on the cardinalities of these three sets. And then we get that this is S. So then we can subtract an S from both sides of these equations and just get 1 over 2n times S is less than I over I to the n times this whole thing. Divide that out, and we get our final proportion that we wanted. And you also multiply the 2n to the other side. Oops. And I actually made a little typo here. That should be a 1, because we're factoring this n out of here and moving it here, and we're also moving this n over to the other side. Cool. Then, as I said before, we know from this definition of S that B is a subset of S union W union M. So the size of B is less than the size of S plus the size of W plus the size of M. It's less than this whole thing, which then if we just do all this magic again, we can get that the size of B, the proportion of bad points in I, is less than 3n squared plus times epsilon plus delta plus 1 over I. Cool. And if we go back to what we were trying to prove, this is exactly what you said. Epsilon prime is equal to 3n squared plus epsilon plus delta plus 1 over the size of I. And so this does prove that G epsilon prime approximates A, because we literally just proved that the proportion of bad points in I to the n in our whole space is less than this quantity. Okay. Alright. Now we get this pasting lemma. So we're going to induct later on the dimension of a subspace. So we're going to start with our one-dimensional subspaces, which are lines. That's the name. And then we're going to build up. Excuse me. We're going to build up part by part to two-dimensional subspaces, three-dimensional subspaces, etc. And the way we're going to do that is by taking, for each subspace, we're going to consider its hyperplanes, which are like the subspace, the n-1 dimensional subspace. And we're going to say, okay, if it's delta linear on most lines in the subspace, and it's 1/10 linear on like some fraction of the hyperplanes, then we get that A is 1/2 multilinear on the whole subspace. In fact, let me actually just write that it's multilinear on the whole subspace, because I think that's a good thing to know. Okay. On the subspace. Okay, cool. And then once we have this, then from self-improvement, we get that A is epsilon prime multilinear, where epsilon prime is that thing we defined in the self-proof lemma. Okay, so the actual statement of this lemma is first you say, okay, we have some A from our space to rational numbers, then we set our parameters so they have a certain relation, but note it's not that crazy. It's like epsilon and delta are polynomially small. Uh, is at least as big as 40 times n. We can definitely do that. We're going to want, when we set the finite field, the prime to be exponentially big in n. So this is fine. Um, and we're still assuming that the proportion of wrong lines in any direction is less than epsilon. Okay, cool. Then we make this additional assumption, right? So the wrong proportion of wrong lines assumption is this delta linear on most lines. And then assume that this set, which is basically saying the set of gamma such that the hyperplane through that gamma, so gamma is just a number in I, not an I to the n, just an I. So the p gamma is going to be I to the n minus 1, right? That's the dimension. Or it's going to be an n to minus 1 dimensional space. That's a hyperplane. So, and we're saying that set phi contains all the gammas such that A restricted on the hyperplane passing through gamma is 1/10 approximately multilinear. Okay, cool. And we're saying that at least a good number of them are like this. So a good number of the hyperplanes have this, and by a good number we mean like more than 1 in every 10n. Okay, this is a little dicey, but we'll see why we're making this assumption later. Then we're going to claim that A is 1/2 multilinear. Okay. This proof, I think, is maybe the most confusingly presented in the original, but we're gonna work through it, and I think we'll get it. So, by the first assumption, right, that most of these lines are the only delta. There's only epsilon fraction of delta wrong lines. We actually get that there's these two functions, f1 and f2, which are functions from n minus one, I to n minus one. Maybe I'll even write that in a little bit. Like these are like from like I to the n minus one to q. Let me write that actually vertically. Okay, yeah. Such that this function, so x f1 of y plus f2 of y, epsilon plus delta approximates a xy. So x is just a number. Y is this n minus 1 length point, by vector, I guess. And we're getting this quantity. There are functions that make this epsilon plus delta approximate A. And what I want to be clear about here is that f1 and f2 are not linear. We're not assuming anything about that. We're just saying that they are functions. And that actually that makes it a lot clearer to me. Um, because if you consider the line like through all the gammas for some fixed y, you can basically you have a 1 minus epsilon delta linear. And then if it is, then you just figure out where, just, set f1y and f2y. Because it's delta linear, it's delta approximated by some linear h, which you can write h as, mx plus b, and then you just set f1 of y equal to m and f2 of y equal to b, and then you're done. So that's totally fine. That's okay. We understand that, and that pretty clearly has this epsilon plus delta approximate feature, because epsilon of the time you get a delta wrong thing, and the rest of the time there's a delta chance that each of these points are wrong, but other than that, you're going to be equal to AXY. So now we're going to define psi, which are kind of these bad points. These in some sense the planes where our function is not close, or yeah, yeah, right. I think that's a good way of saying it. It's these planes where our approximation doesn't work. It's less than 1/10 approximate. Um, then we get this thing where the proportion of the bad points in in I, because I, there's only the size of I many hyperplanes, um, is less than epsilon plus delta over 1/10, or 10 times epsilon plus delta. And that's just, you can see that because otherwise this wouldn't be true, right? Like if it was wrong on more than 1/10 of this, then you would get that f1y plus f2y is not epsilon plus delta approximate, or it doesn't epsilon plus delta approximate a on the whole space. And really the only reason we need that is because we want there to be two things, two elements, two planes, where they're in our set phi, so they have they are 1/10 multilinear, and they are 1/10 multilinear, 1/10 approximated by our function f1 plus f2. So they're not in our set psi, and our set psi is things that are not 1/10 approximated. So they are 1/10 approximated by this thing. Okay, so phi minus psi is, the size of that is greater than the size of I times 1/10 plus, this whole thing. And because of the way we set our parameters, this is greater than 2. Great. Okay, so now let gamma 1 and gamma 2 be in this set. So they are is 1/10 approximate, and it's not in this bad thing, not badly approximated by this. And right. Okay, maybe I should take a little step back here. What this psi is talking about is whether it's approximately multilinear on the planes. Whereas what this is talking about sort of is we've guaranteed, when we're building it, we've kind of guaranteed some linearity in in a certain direction. Like let's say all our lines are going in this direction. So we've guaranteed this linearity in this direction. And this is showing that actually there's some linearity on our functions f1 and f2, even though we didn't assume it was there. Just by the nature of the space and the nature of the function a, we have this approximately multilinearity on two planes that are going like this. So we've constructed linearity in this direction, and then our planes are kind of up in this direction. And maybe that is a good way of thinking about it, because intuitively this is kind of like stitching them together, right? You have two planes where our functions happen to be approximately multilinear here, and then you have all these lines going through them where they've been constructed to be linear. So it makes sense that maybe by treating these two planes as the basis of our approximation, we're going to closely approximate our original function. And that's exactly what we end up doing. So we're going to call g1 and g2 the functions that approximate, basically, for gamma I, g1 times y plus g2 times y, 2/10 approximates gamma I f1 times y plus gamma I of f2 times y, right? And this has to exist because 1/10 of the time, a is equal to gamma of f1 plus f2, gamma times f1 plus f2. And 1/10 of the time, a is equal to gamma of gamma G1 plus G2. So you get 2/10 of the time by union bound. Okay, so then of our subspace, we have that f1y is equal to this function of the g1s and g2s. And g1 and g2 are multilinear. I think I skipped saying that, but this is a key point. And we're getting that they're multilinear. They're these multilinear functions that approximate these hyperplanes. Okay, so on 6/10 of our subspace, we have that f1 is equal to this function, which is also multilinear, right? It's a linear combination of linear functions. And f2 of y is equal to this whole thing, which is again multilinear. So these two left-hand sides are multilinear. So we'll call them f hat 1 and f hat 2. And then we get that x f hat 1 plus f hat 2, 4/10 approximates x f1 plus f2, right? Which, because that's exactly what we said, 6/10 of the time this is true, so 4/10 of the time it's not true. At most 4/10 of the time it's not true. And we know that this 1/10 approximates A. So x f hat 1 plus f hat 2, 4/10 plus 1/10 approximates A, which is 1/2 approximates A. Great. And so then you get from this, you then get, using the self-improvement lemma, that actually epsilon prime approximates A. Okay. Wow. I'm really happy about that. So we're getting there. We're almost done. We're just going to go through the actual structure of this induction argument now. So we start with again our function A, and this assumption that the proportion of delta wrong lines in any direction is less than epsilon. And then our claim is that A is epsilon prime approximately multilinear. And again, we set our parameters in this certain way. So the way we're going to do this is we're going to construct this tree of subspaces. And the root is in, so it's the whole I to the n, it's the whole space. And each node has its children of all of its hyperplanes. So the children of I to the n will be all of the n-1 dimensional subspaces, and then the children of those will be their respective n-2 dimensional subspaces that are subsets of the larger space. And you can see that this is a tree. I'll leave that as an exercise so you can convince yourself. And the tree has depth n-1, because small subspaces are one-dimensional. The biggest one is n-dimensional. And level k, if we treat level 0 as the leaves, holds like k plus 1 dimensional subspaces. And the leaves hold lines, right? So level 0 holds leaves, which are one-dimensional subspaces, which are lines. Okay. So what we're going to do is kind of tree coloring. And it's not really coloring like graph coloring, it's just a way of keeping track of a certain property on our tree. And the first thing we're going to do is coloring the leaves that are delta wrong white. So the leaves that correspond to a delta wrong line, I guess is what I should say. Color them white, and color the rest of them red. Then the proportion of red leaves is, of white leaves, I should say. White leaves is, and it's less than this epsilon by our assumption. Then we color the tree according to this rule. So we say a vertex is red if and only if these two criteria hold. So almost all leaves in its subtree are red. So, and what we're going to say is less than a 2 epsilon fraction of them are white. And a fair number of children are red. So at least 1/10n a fraction are red. And I hope you can see where this is going. So we say here, oops, we say almost all leaves and a fair number of children, right? And if we go up to our pasting lemma, we have like, okay, it's linear on most lines and on a decent fraction of hyperplanes, and we have this, it's kind of applied the same way. Um, and what we're going to end up doing is we're going to make these two claims. So the first claim is that red vertices mean that the corresponding subspace is 1/10 approximately multilinear. And then we're going to prove that the root is red, right? So I to the n is red, and that will complete our proof. All right. So first, proving this fact. So we're going to induct on k, which is the dimension of the subspace. So k equals 1 is obviously okay because delta is less than 1/10, right? Um, right. Yeah, k equals 1 is, yeah, sorry. So k equals 1 is okay because what that corresponds to is saying that a line is 1/10 approximately linear, and we know that red lines are delta or not delta wrong, so they're delta approximately linear, and we know that delta is less than 1/10. Then for k is greater than 1, we start with the inductive hypothesis, which says that red children are 1/10 approximated. And we know that at least 1 in every 10n children are red. So there, we can pick a direction where at least 1 in 10n fraction of hyperplanes in that direction are 1/10 approximately multilinear. And since the root is red, the proportion of wrong lines is less than 2 epsilon. And so this is just setting us up to use the pasting lemma. So in any direction, at most n epsilon fraction are wrong, right? If we get really unlucky and all of our wrong lines are in the direction our hyperplane is going, we get n epsilon. So then from the pasting lemma, the subspace is epsilon star approximately multilinear, where epsilon star is this 3n squared times n epsilon 0, or sorry, it's just, I'm making some typos here. So this should actually be 2n epsilon. We have 2 epsilon wrong lines, so 2n epsilon. And this should also be 2n epsilon. But in any case, this is okay because we've picked these parameters such that this is less than 1/2, and then from the self-improvement lemma, we basically are done. Or actually, sorry, I shouldn't quite say that because the self-improvement lemma has a certain assumption about the proportion of wrong lines, but this is definitely less than uh, 1/10 because of our things, and so then we can keep applying this. Keep applying this claim inductively and complete. All right. So as I said, now we just need to show that the root is red. Okay. So for ease, we're going to call 1/10 phi phi. God, I really need to decide how I'm pronouncing things. And let epsilon not be two times epsilon. So then our conditions on our tree can be restated in sort of a more purely tree form as v is red if and only if less than epsilon 0 fraction of the leaves in the subtree rooted at v, so tv's leaves, are white, and at least phi fraction of these children are red. Okay. So what we're going to actually prove is with this epsilon k, which is equal to 1 minus phi to the k times epsilon naught, we're going to prove that if v is on level k and less than epsilon k fraction of t of the leaves in this tree rooted at V, the subtree, so TV, that's what I mean by that, are red. Then V is red. God. White, right. Um, this is something that might worry you, like 1 minus 1 10 to the n seems like it might be get better, bigger than 1/2, right? But it doesn't. You can prove that pretty quickly. Um, and to prove this statement, we're going to induct on K. So if K equals 1, then we get that this is a 2D subspace, so the children are lines. And the proportion of white leaves is, less than epsilon 1, so and that's less than epsilon 0, so we're totally fine. The proportion of red children is greater than 1 minus epsilon 1. We know that's the inductive hypothesis, right? So um because white leaves and children are the kind of the same. So uh then if we substitute this out, we get that this is equal to this quantity, which is equal to this quantity, and then you can do a little algebraic manipulation to see that this is actually greater than phi. And I'll leave that algebraic manipulation to yourself. I wrote it out here. If k is greater than 2, then again we have that epsilon k is less than epsilon 0. So the proportion we needed of lines, uh, our inductive assumption is that less than delta k or epsilon k of the lines in our subtree are white, and we know that that's less than delta epsilon 0. So this first protocol is we don't need to worry about. We only need to worry about the second thing, which is proving that at least phi fraction of our children are red. And what we actually do here is a probabilistic argument, which is kind of interesting. I tried to see if we could avoid this because it feels kind of I don't know. It introduces a thing that I feel like seems unnecessary, but I didn't see an easy way of getting around it because it uses this Markov's inequality. Okay, so the argument is you pick a random child U of V. Then we know that the expectation of the measure of white leaves in the tree rooted at U is less than epsilon k by our assumption, because this is the number of white leaves of TV, and you take the union of all of these white leaves and you get the number of white leaves in TV. So this is true. Then you can use Markov's inequality to get this, that the probability of all the children that the measure of white leaves in TU is greater than epsilon k minus 1 is less than this. Cool. So that's Markov inequality. And then from the inductive hypothesis, we know that like if this is true, then this is actually like a stronger statement than saying that U is white. Because if this wasn't true, then we know that U is red. So we get the probability, and that's just by the inductive hypothesis, because this not being true means that like this is not true, right? So that means that more than an epsilon k fraction of TU's leaves are white. So then, you know, anyways, uh, yeah, I think you get it. So then we get that this probability here, which is the probability over all U that U is white, is less than 1 minus phi, which then means that the probability that U is red is greater than phi. So the proportion of red children is at least phi. So great. So I to the n is red. So because of that, it's epsilon approximately multilinear. So we could officially verify that A is epsilon prime approximately multilinear. So our final test and sum check passes. So MIP equals NX, right? Only 90 minutes later, you get this great result. Um, pretty unsatisfying to you, and I understand. I think this result is pretty by far the bulk of it is this final multilinearity section, which kind of doesn't I don't know, it doesn't really is it's almost divorced from interactive proofs in the way we think about them. But this is often how complexity theory goes, right? You the complexity theoretic arguments go quickly, like Sharp-SAT is an IP, and then what remains is to use, the non-complexity theoretic sort of not idiomatically, I'll say, complexity-based results to prove these other things. I really encourage if you like this. First of all, what I would love is for more people to make to make lecture notes and lectures on this because I don't think I did the best job that's possible. But I hope by putting this out here, I make it easier for other teachers to make better videos and better lecture notes. So if you can do that, I highly encourage that. And if you're interested in more of this kind of stuff, I recommend reading the original paper. It has its issues, but it's good, and you can certainly work through it all. Um, there aren't that many other sources available, but if you're interested in more stuff like this, I really recommend trying to learn a little bit about quantum and looking into what I consider kind of the culmination or the end of these results, which is the proof that MIP star, which is multiple interactive provers with quantum entanglement between them, is equal to RE, so it can solve the halting problem. Yeah, that's about it. Thank you so much.